Okay, in problem one, we have colors of automobiles at the used car lot, and that's categorical because categories would be like blue and green and white, and that's multinomial since there are more than two groups or two categories. And your text calls that qualitative instead of categorical. I think, well, both names are appropriate. I like to use categorical. It just sounds a lot different than quantitative. Remember, quantitative are things that are numerical, like how much or how many, and categorical are just putting things into groups or categories. So in the quantitative discrete, we just have things, probably best to think of it as things that we count: one person, two people, three people, one car, two cars, three cars, continuous things that we measure on a finer scale or that we could measure on a finer scale. Something like weight. You might think about 100 pounds, 101, but you could have things anywhere in between there, 100.0932 or whatever. Even if that's not what you would report, it's a continuous variable if you do that. Okay, and so in the next one, we're asking every 10th customer. So that's a systematic random sample because we have a random start and then select every nth item. And draw, just as a review here, draw you a little bit of a picture. If we had a random sample, we might have a population that looks like this. Just a bunch of people here. I'm going to draw them in. Bunch of people or whatever it is that we're doing. So in a random sample, we would just randomly select people from that population. That would be our simple random sample. And so if we had a stratified random sample, that would mean that we have some characteristic that differentiates one group from another. And this could be upper and lower classmen, male and female, or whatever. And we want to take a random sample from each population. So now we're going to get 5 from this one and 5 from this one. So we have basically two populations in this case. Like I said, it could be male and female or whatever, and get a random sample from each group. So that's stratified. So that's simple, random sample, stratified, and then cluster would be that we have some natural grouping. And see here, it may be males and females again, but they're randomly distributed throughout the population. So here what we do is we might divide the entire population into 4 clusters. And we're thinking that each one of the clusters has similar characteristics, and then just choose one cluster. Maybe we get this one and just sample everybody in that cluster. That could be like everybody on a city block, could be everybody in one particular elementary school, could be everybody in one particular classroom. Of course, if we had done this with more clusters, maybe we have 100 clusters, we might randomly select 5 of those clusters and everybody within them. And then, of course, the other one we had the systematic. We just have people in there, and then if we have every 10th person, we start at the 5th, we would go to the 5th person. And then, I'm sorry, if we had every 5th person, then we would do something like this. I may be counting wrong, but get a systematic kind of thing. Every 5th person or every 10th or every nth, whatever you want to do with that. Okay, so in the next one, we have a drug test that's 99% specific. That is, it will correctly identify a drug user testing positive 99% of the time. Also will identify a non-user as testing negative. That means that correctly 99% of the time. And so we're going to test employees for drug use, and 0.5% of the employees actually use the drug. So let's start with that we have 0.005. That's 0.5% that use the drug, or that use the drug, and that would leave 0.995 that don't use the drug. So if they don't use the drug, we get a negative test that says they don't use the drug 99% of the time, and a positive test 1% of the time. And if they are using the drug, we get a positive test 99% of the time. They do use it, and it says they do, and a false 1% of the time, a false negative. So now what we're saying is they have a positive test. So we're down to they didn't take a drug and they have a positive, and they did take a drug and they have a positive. And we can multiply across and get these probabilities. So again, we have a drug use rate of 0.005, and that would, if it's right, will lead to a positive test, and it does that 99% of the time. And then 1% of the time it will incorrectly give a negative result. And then on the bottom here we have someone who's not a drug user, and that's 0.995 of the population. And of those, you'll get the correct decision, that is that they have a negative test, 99%, and a positive test, 0.01 or 1% of the time. So we're starting with, we only want to get the ones where we have a positive test, and I've gone ahead and just computed the probability, just multiplying across the branches where I had positives. So I have someone who uses the drug and gets a positive result, and someone who doesn't use the drug and gets a positive result. So those are, everyone I'm interested in now are those who got the positive result. And so here we go. I got the 0.00495, got a positive result, and they should have, divided by 0.00495. That's the probability they got the positive result and should have, and 0.00995, which is the probability they got a positive result and shouldn't have. So even though they got the positive result, and it's a 99% chance that they got it right when they did have a positive result, because there's so many more people that don't have it and get a false positive, only 1/3, there's a 0.332 chance of an employee actually being a drug user if they got the positive test.